Hello, Physics Chinese. Today I'm going to finish the lesson on Newton's first law of motion by solving a third example problem. Third example problem that's quite a bit more difficult than examples 1 and 2 from which I solved in the previous lesson. And let's just jump straight into it. So what I have is a 10 kilogram sign. It's being held in place by two cables. I'll start off by labeling these cables. We'll call this cable on the left cable 1. We'll call the cable on the right cable 2. And I'm going to label these angles. We'll call the 45-degree angle theta 1. And we'll call the 30-degree angle theta 2. What I want to do is I want to draw a free body diagram of the sign. Then I want to write down equations of motion in the x and y direction, and then calculate the magnitude of the tension in each of these cables. And to do that, we're going to need to solve a system of equations. Part A. FBD, free body diagram for the sign, would have force of gravity straight down, Fg. You'd have a tension force due to both those cables. So one of them is going to go up and towards the left. We'll call this one Fa1. And we have another tension force that'd be up and towards the right. We'll call this one Fa2. Now, this would be a complete free body diagram, but because it's useful in the analysis, I'm going to draw the vector components. Albeit you're not technically supposed to draw them on an FBD, but I'll compromise by drawing with a dashed line. So Fa1 would have an x component that points towards the left. So we call it Fa1x. It'd have a y component that points up, which we'll call Fa1y. And this angle here is theta 1. Fa2 would have an x component that points towards the right, a y component that points up. We'll call the y component Fa2y, and the x component Fa2x. And we'll label that angle as theta 2. And that is my free body diagram. Now, part B. Let's go to the equations of motion. Start in the x direction. Let's assume right is positive. So find the sum of the forces in the x direction. If we're in a state of equilibrium, that's equal to 0. Okay, now what this means, again, is look at the free body diagram, look at the forces in the x direction. If the force points towards the right, we're going to write a plus sign in front of it. If it points towards the left, we're going to write a negative sign in front of it. So this would then become positive Fa2x, because Fa2x points right, which is positive. Subtract Fa1x. Fa1x points towards the left, therefore it's negative. We can expand this one step further. Fa2x would become Fa2, cosine of theta 2. Subtract Fa1, cosine of theta 1, and that's equal to 0. Now, you may have noticed already, let's block this equation first. You may have noticed already that the FBD is pretty much the same thing as example 1 for a hanging picture frame. The big difference right here is these angles are not the same. And you can see in equation 1 the complication. So for the picture frame example, from example 1, because the theta values were the same, we were allowed to cancel the cosines off, which just told me the magnitude of the tension in both wires was identical. We're not going to be able to do that here. That's going to make things tougher. Now let's go to the y direction. So find the sum of the forces in the y direction. And if we're in a state of equilibrium, which we are, specifically static equilibrium, that sum is going to be 0. So what this means is look at all your forces in the y direction. If they point up, put a plus sign in front of them. If they point down, put a negative sign in front of them. So we have 3 forces in the y direction. We have Fa1y, which points up, therefore it's positive. Fa1y. We have Fa2y that also points up. It's positive. Fa2y. Fg points down, it's negative. And that's equal to 0. We can expand one step further, where I would have Fa1 times sine of theta 1 plus Fa2 times sine theta 2. Subtract, force of gravity is m times g, and that's equal to 0. Box this equation, and we'll call it equation number 2. Now, the reason we have a system of equations is because we have 2 equations, and in both these equations, we have 2 variables that are unknown. We don't know what Fa1 is, and we don't know what Fa2 is. However, if you have 2 equations and 2 unknowns, you can solve the system. And that's what I'm going to show how to do in part C. Let's start off with equation 1. So equation 1 was Fa2 cos theta 2 subtract Fa1 cos theta 1 is equal to 0. I'm going to add Fa1 cos theta to both sides of the equation. So I then have Fa2 cos theta 2 is equal to Fa1 cos theta 1. I'll do one more step right here. I'm just going to isolate Fa2. So I'll divide both sides of the equation by cos theta 2. And then I would have Fa2 would be equal to Fa1 cos theta 1 divided by cosine of theta 2. I'm going to box this equation, and I'm going to call it equation 3. Now, I'm going to rewrite out equation 2. So equation 2 was Fa1 sine theta 1 plus Fa2 sine theta 2 subtract mg, and that's equal to 0. Now, what I'm going to do right here to solve the system is I'm going to use a technique called substitution. The way this works, let's pick a different ink color here, is I know Fa2 is equal to this expression, Fa1 cos theta 1 over cos theta 2. So what I'm going to do is I'm going to take this expression right here, and I'm going to replace Fa2 with Fa1 cos theta 1 over cos theta 2. And I'll just clarify what I'm doing right here. I'm going to sub equation 3 into equation 2. Okay, so let's see what this looks like now when we expand it. This would now become Fa1 sine theta 1 plus. Now, I'm going to write the expression I'm substituting in a different color. So I'll put this in purple. So this would then be, and I'll put it in brackets, FA1 cosine theta 1 over cosine theta 2. So that's what I'm subbing in for FA2. Do the rest of the expression in the red color, times sine theta 2, subtract mg. Actually, you know what? Let's move the mg over to the other side, and we'll say just equal to mg if we add mg to both sides of the equation. Now, this looks a little bit tricky to deal with initially because I now have a denominator. I now have a denominator of cosine theta 2, and if I want to solve this correctly, I would technically need to get a common denominator for every single term, but I really don't want to do that. So there's actually a trig identity we can sub in here that will allow us to avoid having to deal with a complicated common denominator. Well, I shouldn't say the common denominator is complicated, it's just annoying to deal with. So here's what I'm going to focus on. I'm going to focus on this. Sine theta 2 over cosine theta 2. Now, this is a trig identity. I think you start to learn about this in Math 20-1. If you don't know about this, it's not a problem. I'll just simply tell it to you right now. Anytime you take sine of an angle and you divide by cosine of that same angle, that is equal to tangent of the angle. If you don't believe me, you can take any values of theta, plug them in, go sine, for example, sine of 60 divided by cos of 60, and then compare that to what tan of 60 is equal to, and they should be the same numerical value. So let's rewrite this equation now. So this would then become FA1 sine theta 1 plus FA1 cosine theta 1. We're going to replace the sine theta 2 over cos theta 2 with tan theta 2. And then that is equal to m times g. So we now have one equation and we have one unknown. So that's FA1. Now I can't solve for FA1 yet because it's in two terms. So to get it kind of separated, I'm just going to factor it. So if I factor FA1 out of both terms on the left-hand side of the equation, you'd then be left with sine theta 1 plus cos theta 1 tan theta 2 is equal to mg. To solve this equation, you're just going to divide both sides of the equation by everything in those brackets. So that's going to give me FA1 would then be equal to mg divided by sine theta 1 plus cos theta 1 times tan theta 2 and now we plug numbers in. So m is 10 kilograms. G is the magnitude of the acceleration due to gravity. That is 9.81 meters per second squared. Divide this by, let's put everything in square brackets at the bottom right here, just because we have multiple terms in the denominator, we don't want to mess the order of operations up. So theta 1 was the bigger angle, so that's 45 degrees. Plus cosine of theta 1, and theta 1 is 45 degrees, times tan of theta 2. Theta 2 is that smaller angle, which is 30 degrees. And this is now going to be equal to, when we plug this in, so I believe I should get an FA1 value that is going to be 88.0 newtons. Let's just write that down in a separate line here. I'm just going to erase this. Okay, so FA1 would then be equal to 88.0 newtons. Now, it turns out it's actually really easy to solve for FA2 because we have an equation that is already isolated for equation 2. That's this one right here, equation 3. So all we need to do is just plug in the value of FA1 into equation 3, and we can solve immediately for FA2. So this would be FA2 would then be equal to 88.0 newtons multiplied by cosine of theta 1. Theta 1 is that bigger angle, so that's 45 degrees. Divide this by cosine of theta 2, which is the smaller angle, 30 degrees. And then I get FA2 would then be equal to 71.9 newtons. Okay, so that's how you solve a system of equation using substitution, and hopefully that'll help you in completing the next assignment on Newton's first law of motion, part 2. Thanks.